Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. In the previous lecture we have seen how the property of controllability suffices in allowing us, in enabling us to place the closed loop poles of a system through a linear state feedback to any location in the complex plane that we desire, right. In other words, we can shape the characteristic polynomial, the closed loop characteristic polynomial of a system through state feedback in any manner that we please, provided the system is controllable. Now you might wonder, isn't that an overkill? What is the guarantee that I will not be able to do this if the system is not controllable? Yeah. So far I have only outlined a method before you and I have shown you that if it is controllable, then you will be able to place the poles. But what if it is not controllable? What if your realization is not controllable? What is the guarantee that you will not be able to place the poles? After all, from the definition of controllability we have seen thus far, it is just the ability to sort of get from one position in the state space to another. So one state to the other in any amount of time that is given to me through some suitable input. That has got nothing to do with pole placement directly as of now, right. But it will turn out that this ability to sort of go from any point in the state space to another, yeah, and this ability to place your poles anywhere in the complex plane, these are both contingent upon the controllability of the system, yeah. So of course we have shown you the sufficiency in the previous lecture. We have convinced you that in case of a single input single output system, if it is controllable, the realization that is, then there does exist a unique set of gains, yeah, which allow you to design a state feedback, a linear state feedback that will place your poles wherever you like, wherever it has been specified. But now we will see that if your realization fails to be controllable, then on the other hand there will always be some poles which you cannot place at will, yeah. Those poles are like the stubborn fellows, this obstinate poles that do not budge an inch no matter what input you apply to your system, right. So to convince ourselves of this fact, we will again resort to taking a matrix to its Jordan canonical form, yeah. I do not want to go into other sort of linear algebraic tools. One tool is enough and it will turn out that even though in some cases it is not the most convenient tool, but it will still suffice to convince you that, well, if you have this T, then T inverse AT, there always exists such a T inverse such that you can take this matrix A, any square matrix A, to a Jordan form, and correspondingly the B matrix will be transformed to T inverse B, yeah, the T inverse B, yeah, right. So what does the typical Jordan form look like? We have seen that lambda 1, lambda 2 till lambda r, that is one sort of a Jordan block, yeah, again at the cost of being repetitive and boring, yeah. This is another type of Jordan block. Of course there can be many more such blocks, I am just drawing one typical sample of each. Then there is this A minus AB, sorry, the way I have drawn it is probably AB minus BA, yeah, it does not matter, you can allow B to have any sign and it does not matter really. That is one type of Jordan block, yeah. Then there is another type of Jordan block, you can have these in this complex poles also repeated, right. So A, B or A1, B1 minus B1, A1, then A1, B1 minus B1, A1 and then I2 here, right. So you can have this type of a Jordan block as well, Yeah. So we have seen when does this system fail to be controllable, when either if you look at the A matrix and you find that in this diagonal block some diagonal entries are not distinct. Yeah. So when some diagonal entries are not distinct, we have seen that it loses controllability and therefore also minimality by extension, right. Okay. So what happens when some diagonal entries are not distinct? Consider only this small block here, because these blocks are decoupled. I am going to just consider the small block here that corresponds to this. So this is of size R. So the first R entry, so this is BR. So T inverse B, I am only considering the first R, and this T inverse AT, I am considering the first R cross R block, okay, this block. So what does the structure look like? Now you notice that suppose this structure looks like lambda 1, lambda 2 till lambda R, and suppose you have this B matrix, this T inverse B, which also has some entries B1, B2, BR. Suppose these are non-zero, yeah. So of course if one of them is 0, then you immediately see that the dynamics is not at all affected by U, yeah. So first let us start with the easy observation. Easy observation is look at B. We'll get back to A later. Yeah, we'll get back to A later. So when does a system in the Jordan canonical form fail to be controllable on account of the structure of B? When for this diagonal block any one of these entries is 0. So if any one of these entries is 0 here, what happens? You see that particular system's mode, that particular eigenvalue, yeah, that particular system's mode will be xi dot is equal to lambda I x, and no matter what input you apply, it will not be reflected here. So clearly whatever gains you might design or whatever, it is not going to affect the dynamics of this mode, so it is going to remain uncontrollable. Similarly, if when you look at a block such as this, if both of these B entries are 0, yeah, both of these entries in the corresponding B matrix are 0, so if you have A, B minus B, A, and you have 0, 0, yeah, if this is your A and this is your B matrix, yeah, then obviously nothing that you apply at the input channel ever gets passed on to the states, so it is going to be uncontrollable. You cannot place these poles. Whatever state feedback you might apply will fall flat on its face, because it is not going to affect, because 0 times k is going to be 0. It is a no brainer. Similarly here you see, if in this block Jordan form, if any of these last two entries of the B matrix, yeah, if both of these last two entries of the B matrix are 0, then what happens? Nothing can affect these modes, yeah, same thing as the earlier case, right. So this is going to lose controllability, yeah, and because it loses controllability, at the same time you will see it loses the ability to place the poles, or you lose the ability to place the poles, because no matter what you apply at the input, after all you are only placing the poles through a state feedback applied at the input. So if the input itself falls flat on its face, nothing is changed, right. So you cannot influence those particular poles, at least this last two pair of complex conjugate poles, yeah. Similarly here also in this block, if the last entry happens to be 0, then at least this pole, the others might be placeable, I do not know, but at least this pole cannot be placed, yeah. So therefore you see that the moment every condition that you see in terms of the matrix B that is tantamount to lack of controllability also leads to loss of the ability to place those certain poles or the other. So whenever you lose controllability by one of these factors or the other, by some entries of this B matrix being of 0 value or the other, it also immediately brings with it, like a combined package, your loss of the ability to place certain poles, right. So therefore loss of controllability leads to loss of poles, pole placement ability, right. What about the A matrix now? We have seen that in the A matrix case, the controllability and as well as both observability can be lost if in the real diagonal block any two of the eigenvalues happen to be identical, or in the complex diagonal block any two of the complex diagonal blocks happen to be identical. So that complex diagonal block happens to be identical, leading to lack of controllability and therefore leading to lack of pole placement ability, yeah, if there is a term like that I leave to you as a proof, but I will show you at least why. So suppose if there is a diagonal, so I will show you why in the block diagonal case at least, if any two of these fellows happen to be equal, then you will not be able to place your poles even if all your B entries here are going to be non-zero. So let us say this is B and this is A. So I am just going to look at the small block here. So without loss of generality, let lambda 1 is equal to lambda 2. Then look what happens. And suppose your K matrix is K1 dot 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 till Kn. So then what happens? Look at A plus Bk. A plus Bk is basically this lambda 1 times 1 0 0 0. You agree this is that part that is coming from A, that is the first row, right, plus B1 times K, you agree. The second row is lambda 1 times, because lambda 1 and lambda 2 are equal, times 0 1 0 0 0 0 plus B2 times the same K. Yeah, if I am just looking at the first row of the A plus Bk matrix, yeah, then this is what it is. Now we have assumed that lambda 1 is equal to lambda 2. Now notice what I am going to do is I am going to find the determinant of this, or rather, excuse me there. So what I am going to do is I am going to actually find the determinant of lambda I minus this, because I want to find out the characteristic polynomial. So this will require me to basically find out the lambda I minus this whole fellow's determinant. Sorry about the atrocious notation here. So this is what I am trying to do. So I do not care about the other columns, let us just focus our attention on the two entries of this diagonal block which are equal. What happens then? Now you notice that this is going to be nothing but, well, what is this lambda I? So now I am going to write the first two entries. So this is going to be determinant, this big matrix, you see it is lambda minus lambda 1 times 1 0 minus B1k, and this is also lambda minus lambda 1 times, but the vector is different, 0 1 0 dot 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 minus B2k, right. Now if I want to find the determinant of this, you see what I can do is, if determinants are invariant to row operations, yeah. So what I can do is, in row 1 I am going to change as row 1 minus B1 by B2 times row 2, okay. So row 1 I am going to change as B1 minus row 1 minus B1 minus B2 times row 2, and I am going to place it back. So what happens then? So this is going to be equal to, so just refresh your knowledge of determinants, if you have forgotten the operation of determinants, then this is how we do it. So what then happens? We have lambda minus lambda 1 times 1 0 0 minus B1k minus B1 by B2, again lambda minus lambda 1 times 0 1 0 plus B1k. So this B1k and B1k will cancel out. What am I left with then? You see, from the whole of this row I can take this factor out common, lambda minus lambda 1 out common, and then I am left with this determinant. I do not care about the second row anymore, the second row I have retained as it is anyway. So this is my R2, yeah, this is my R2, this is my R1, yeah. So the second row I have retained as it is, the first row I have changed operation, and now I am taking this lambda minus lambda 1 out from the common from the first row, because I can, right, determinants again, that is a determinant, standard determinant operation. So what happens then? Then this is going to be nothing but this 1 dot 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 0 minus B1 by B2 times this 0 1 0, yeah. So therefore you see, no matter what the rest of the determinant evaluates to, this is always going to be a factor of this determinant. So this is a factor of the characteristic polynomial of a plus bk. Now that means that lambda 1, whether I like it or not, is always going to be a pole of the closed loop system, so lambda 1 was the pole of the open loop system, and lambda 1 will also continue to be a pole of the closed loop system, and that is only happening because I had some repetition of eigenvalues or repetition of entries in the diagonals of this diagonal block, which is tantamount to loss of controllability. So loss of controllability tells me it is also going to lead to my loss of ability to place this particular pole which was repeated in the diagonal block, right. So therefore at least I hope to have convinced you that whether you lose controllability due to the structure of the B matrix or you lose that because of the structure of the A matrix, I haven't tackled the complex block, of course, that I leave to you as a homework, but whether you lose your controllability owing to the structure of the B matrix or owing to the structure of the A matrix, yeah, it is always going to lead to your inability to place some pole or the other, right. Some of those open loop poles will continue to remain closed loop poles, you cannot place them, they are the stubborn ones. So therefore controllability is not just a sufficient condition as we saw in the previous lecture, it is also a necessary condition for your ability to place each and every single pole of the system, right. So that is basically the point that I wanted to highlight, and hopefully I have been able to convince you that the property of controllability is not just important for the ability to take the states from one value to the other, one point to the other in the state space, but also it has a very functional utility in controller synthesis. It is this property of controllability which allows you to design a state feedback, a linear state feedback, which enables you to place your closed loop poles anywhere you like. So that is all well and good, this looks like a triumph of modern control theory, right, a big result. Earlier we were struggling to even stabilize an unstable system using root locus based method, as we have highlighted a couple of lectures back with an example, right. We saw that no matter what you do, if you have a pole on the right half plane and maybe the 0 at the origin, then that particular segment of the root locus, no matter what you apply, any stable controller that you might use, you cannot apply an unstable controller, that will only make matters worse, right. So any stable controller that you might use, whether it is P, PD or whatever, you are always going to end up in a situation where one of your poles are always going to be on the right half plane. So that is a failure in some sense, right, but this is where modern control apparently triumphs. But those of you who are going to nitpick a little more and really trying to find holes in my argument would be quick to point out that wait, you have made a very strong assumption. Earlier you had this system GS and you had this output Y and you had this input here, so you could only feedback this Y. So obviously you are crippling this other mode of design, this classical control method of design was crippled because it was compelled to use only the output, but that is also because I would say that is also because this classical control method does not take into account internal behaviors. But then you might say, well, hang on, you are saying you are accounting for the internal behavior through your state space, but that is actually tantamount to ripping it open, because after all what are you doing, you have this integrator here, yeah, and you have these states coming out here and you pass it through the C and then you get your Y and you fed it back through this channel here, you had this A. So this is your effective state space systems design, no, AX, and you had this is your U coming in here and this is the B matrix. So this is AX plus BU, so this is a plus, yeah, so this was your basic design. But now while designing the controller, ideally what you should have done is you should have tapped in, because this entire thing I have drawn in the red box here is internal to the system, so you should have used some signal from here, but what you instead did was you picked up the signal from here. Not just that, it is not just the fact that you have gone inside the system and picked something out, yeah, and then you passed it through this key apparently, yeah, and then cooked up this thing here, yeah, and then you added it here, and then you are calling this your controller, this green part that you are now drawing, you are calling this your controller, yeah, that is well and good, but you have to admit that you are actually using more than you should be using according to the classical method. You might say that, well, I have described it in a state space form because I precisely wanted that internal description, but who is to guarantee that you are going to always be able to look inside the system and tap in at a point inside the system? What if the wiring is such that you cannot break it open? Yeah, then what do? Then all of this state feedback method that you are singing praises of, yeah, it's apparently no good. But then I want to remind you that we have our old friend, the other property called observability. So you might wonder then, can we not take y dot, y double dot, so on till yn minus 1 derivative, yeah, and from this can we not get our state information? In other words, can we not pass the output through a bank of differentiators? Yeah. So instead of saying that this is how I have designed the controller, if you are not very happy with this, let me just say that I am going to design this as my controller. So this C, then this A, yeah, this comes here, excuse the bad drawing again, yeah, sorry, this is not. So there should be a B matrix here, this is the U and this is the C. So instead of saying that I am going to pass this through, I am going to tap in through this point that is internal to it, let me just say that I am going to just take this Y and pass it through a bank of differentiators, yeah, till there are like n differentiators. So I am going to take this Y as alone, I am going to take this fellow, I am going to take tap outs from here, yeah, and I am going to have these n variables, yeah, and they are going to extract. So then I pass it through this observability inverse and I have the states, but then that vector gets yeah, then that vector gets passed through this k here, yeah. So this is my x now, yeah, through suitable transformation here, this observability inverse will lead to the x here, then that x passes through this, so this kx is going to be another scalar, so that gets added with this, and this is my external input, yeah, right. So now you might say that, well, if you are not happy with me tapping inside, then you keep your box closed, right, keep your box closed, keep your box to yourself, yeah, I do not want your secrets inside the box, okay, let it be unopened. I am going to just take this tap out from here and I am going to pass it through a bank of differentiators, and then again you pick a hole with my argument and say, hang on, didn't you just say a while back, maybe a few lectures back, that it is a bad idea to use differentiators because they amplify noise, yeah. So what is it with this using this same differentiator again? It is a bad idea, no? So your system might have signals at higher frequency, and if there is some noise, right, then if you have higher gains at those noise, as this differentiators clearly would imply, yeah, then the signal will be corrupted with noise, and this x information that you have, the state information that you have, is probably not going to be very useful for your feedback, and yeah, grudgingly I will have to agree. Yeah, you are right, you have caught me there. So then what is the way out? In principle this works, but at a theoretical level, but if you want to really practically implement this, you can't implement it using differentiators. So then what do we do? Remember, when we implemented differential equations, we didn't use differentiators, we used integrators. So can we not use the same thing here? In other words, why not use an open loop strategy like this? What is the open loop strategy? Suppose this is the input that you are giving, is passing through B here, yeah, then it is becoming U here, then it is coming through from some A matrix here, then there is this bank of integrators here which is spitting out the state from here, yeah, then there is this C matrix here which is again giving you this Y. So this is the typical state space diagram, yeah. Now let us say this is the actual plant, this is the actual plant. What if I just use the same signal and I simulate this plant. So I use a model of this plant, I know exactly what the model is going to be like. So let me not draw this again in so much detail, let me just say that I am going to just use a model of this plant. X dot is equal to Ax plus Bu or X hat, yeah, so these are my X hat and Y is equal to Cx hat plus Du. So this is Y hat, yeah, so this is going to give me Y hat. But more importantly, because this is a model that I have created, so I can tap in now. Now I may not be able to tap in, you may not allow me to tap into this actual plant here because you say that there is this box which has to be kept sealed and unbroken, right? You cannot break into the box and tap in at any point you like. So I will say fine, I will not do that. What I will do is I at least have access to the input. So let me just tap in at the input terminal and feed it to a simulated model of the actual plant. Now this model I can play around with as I like, yeah. Of course, then what I have here is that, look, what is the difference between these two then? So X dot is equal to Ax plus Bu and X hat dot is also equal to Ax hat plus Bu. So if I take X minus X hat whole dot, yeah, this is let us say E, the error, then this is going to be what? A times X minus X hat, which is AE. So therefore the error, yeah, so if I tap out of here, what I will get is essentially X hat, remember, and that X hat then I can use for my purpose to pass through a gain here K, and then I add it like here, yeah. So let me say that is my strategy now. So this is what I would call an open loop observer, this model, yeah. But there is a problem with this open loop observer. What is the problem with this open loop observer? The problem with this open loop observer stems from the fact that, well, you see, this A matrix is going to determine the dynamics of this error. But what if this error is non-zero? I mean, I may not exactly know what the initial value of the state of the model and the initial value of the actual system are, right? So then in that case, I will have some initial non-zero error. So then E dot is equal to AE and E0 is not equal to 0. Now suppose, you can immediately now see the problem, suppose the A matrix, that is of course the plant that is uncompensated or uncontrolled. As we have already seen earlier, this plant uncompensated or uncontrolled may be unstable. So if it is unstable, then even if you have a very small non-zero error between the initial condition of your integrators of the model and the initial conditions of the plant, then that error will never converge to 0. In other words, X does or X hat does not converge to X if A is not Hurwitz. So again we say a matrix is Hurwitz, let me introduce the terminology. A matrix A is Hurwitz if all its eigenvalues are in the strict left half plane. So if A is not Hurwitz, then X hat minus X hat does not tend to 0 as t tends to infinity, right. So in other words, this model is no good. What if it is stable? What if it is Hurwitz? Even then we may not be very happy with the rate at which the estimates of these states X hat converge to the actual states of the plant X. What if the poles are very slow? What if the poles are too close to the imaginary axis for my liking, right. So I may want to play around with these poles, but because of this open loop nature of this observer here, yeah, if it is unstable, forget about using this, it does not work. Even if it is stable, but if the A matrix of the plant, of course in the plant I can design the K and hasten the operation of the plant, right, from this R to Y. But in this observer I have no handle over this because this is an open loop system now, this model is an open loop system, no, yeah. So then I wonder, can I also sort of place poles of this observer in a clever fashion, yeah, and then make the dynamics of this fellow also stable. But then what is the guarantee that this dynamics will match this dynamics, right? That is the fundamental principle. If you are designing some, so you see it's like a chicken and an egg problem. If you want to design a state feedback for the original plant, you need the state information of the original plant from this model. But if you want the model's states to actually match the original plant's states, then you need this A matrix to be stable. But what if this A matrix is not stable or not fast enough, its dynamics are not fast enough, then what do? Do you simply make change in the observer model? But then the observer will not match the plant's model. So the whole purpose of this model, using this model, will be defeated. So we seem to be at an impasse, right, at a position where we do not know how to head forward. It is here that we introduce this idea of something called a closed loop observer. So we will introduce this structure of this closed loop observer here. Initially I will just introduce this with the assumption, just like for the pole placement of the controller we assume that it was controllable, for the observer we will assume that the realization is observable. So if you want to use this observer and controller in combination, you better have both observability and controllability. Yeah, maybe I am getting a little ahead of myself, but let me still make that statement. We saw that for pole placement ability, again abuse of term, pole placement ability, using state feedback, linear state feedback, we need controllability, it is a necessary and sufficient condition. Now we see, or we shall see, that for designing a closed loop observer whose dynamics are fast enough and suitable enough and stable, yeah, it will turn out that observability, and I am not going to prove this, it is going to be exactly in the same fashion as we proved or established the condition for controllability. You can take that as a homework, but it will be clear why I am saying this when we are through with this design of the observer. So we will see that this design of this observer, yeah, can be carried out provided the system is observable. So if you are a Puritan and you do not want to tap into the states of the plant, instead you want to use a closed loop observer, extract information about the states and use that for feedback, then you need both controllability and observability. In other words, you need minimality. So if you have a minimal realization, at least then we can be sure that this method works without the usual complaints that you might hurl at me that I am using some tap in inside the system, right. So I am using exactly the same information that I was allowed to in the classical control methods like root locus, and I am still going to be able to do better. I am going to be able to place poles anywhere arbitrarily. Only restriction is that the realization must be minimal, so that the transfer function that I start with, if that is basically irreducible, or if the numerator and denominator polynomials are co-prime, yeah, then I am always going to be able to do this for any realization. That is the big statement that we are going to make right at the end of this, almost at the end of this journey into modern control and its tools, at least insofar as CISO systems are concerned. Okay, so let us see, since we are making all of this claim, what is this closed loop observer structure is going to be, and what is the big idea behind all of this. So here is what it is. For the umpteenth time, let me redraw this, and please bear with me while I do this. So here we have the C, so here we have the Y, and over here we have, of course, the system's A matrix, okay, yeah. So we have this, and we have the B matrix, yeah, okay. So this is our original system, all of this inside a briefcase or a black box that I am not allowed to open. So here is what I do, I take this, I pass it through another B, yeah. So now I am going to give you the detailed structure of the observer here, right. So where is this U coming from? Remember, this U can come from, okay, maybe I will get to that later. First let me draw the observer, and then I will draw the combined observer plus controller structure. So I am going to draw this entire thing here, and then we are going to launch into an analysis of this. Yeah, that will be the really interesting bit where we will see something called the separation principle. Okay, again let us not get ahead of ourselves, let us just draw this figure here. So this of course is going to be again this b times u here, but notice that what we are going to have here is now again this integrator here, again this is a model here. So this is the actual plant, perchance we were to sort of, so this is going to be my y hat, okay, alright, and this is going to be again my A matrix. From this I take in a tap in here, yeah, and I add it here. So once I pass this through B, this also becomes a vector, yeah, so this is all added here, right. Now up until here there is no difference, right, you see that it looks exactly like the open loop configuration, sorry where was that, yeah, this open loop configuration that I had drawn here. So you might wonder where is this loop going to be closed, yeah, and this is where the beauty of this observer comes in, okay. So where are we going to close the loop? We are going to bring this down here and pull this up here, and we are going to take the difference, okay. So this is what we are going to do, we are going to take this plus minus, okay, and this then we are going to pass through. So remember this is a single signal, yeah, this we are going to vectorize through this L here, and L belongs to R to the n, L has the same dimension as B, right. So you pass on a scalar signal through L and it vectorizes it, just like B, you pass on this U signal through B and it vectorizes it to match with this. So then this becomes my this signal, and then this L comes in here, yeah, and this also gets added here, yeah. So this gets added here, okay. So this is the part, this is the crucial part, okay. This is the crucial difference between this and the earlier structure which I had drawn, yeah. This crucial part that I have now marked in green, this is what makes it closed loop. Now of course you might wonder and say that, well, isn't this going to tamper, there are a lot of concerns here, right. First of all, what is the dynamics going to look like, we have to write that down algebraically. The thing is I have drawn this out here because I know that it works, so I have just first drawn it and then we will go ahead and do all our proofs and analysis, yeah. But at this point if you do not have any questions, then you are probably not following the lessons closely enough, right. You should have a lot of questions at this point, like where is this arbitrary structure coming from, who has told me that this, if I take this sort of a feedback, so where is the guarantee that this feedback is going to actually address the issues that were here, which is like if A is unstable or A has poles that are slow, then it is still going to work, right, what is the guarantee. And moreover, my ultimate goal is, remember, to tap out of this models. So this is the model, so therefore I can rip into this model and tap out this state here. So my ultimate goal is to cook up this thing, right, pass it through this K here, yeah, and then this becomes a single signal like this and pass it through a summer here, and then this becomes my R, right. So my U is basically K times X hat, so this is X hat, right, this is X hat. So K times X hat plus R. So this is going to be, this red part I have drawn is now going to be my controller. Of course if you want to talk about the overall controller, then that is going to be everything that is outside this dotted black box. The observer plus this controller combined is the overall controller, yeah. So this is the controller plus observer structure. Now a lot of questions should spring to your mind at this point, right, like am I not tampering with the overall closed loop transfer function between R and Y? After all, that is what I am most concerned with, right, whether this transfer function between from this R to this Y, whether that still remains intact, and whether by putting in this L here I am not messing around with those closed loop poles, yeah. Even what about the size of the matrices, what about the size of the transfer functions, I mean the degree of the transfer function, how many poles are there, a lot of things might pop up to your mind at this point, right, and rightly they should bother you. So that is what will motivate us to do the ensuing analysis, and that is why you will see that this is a stroke of brilliance. The idea of using this observer is actually a stroke of brilliance, right, and then we shall see that even though we are using this observer, at the same time while it allows us to sort of move the poles of this observer of this model and make them fast or stable as we please, which was essentially the problem here, because if A inherently was unstable or slow, then the error would never converge, but the use of this L here, this feedback here, would allow us to place the pole of the observer and thereby ensure that this error will eventually go to 0, this x hat will eventually converge to x, and if this x hat eventually converges to x, then except for the transient phase at steady state x hat is equal to x, and therefore using x hat as an estimate or a proxy for x is good enough. So therefore instead of tapping into the original system, I can tap into the model, which is something I have built, it is my design, so I can tap in anywhere I like, right. So that is the beauty, that please appreciate, try to appreciate the fact that what we are trying to avoid is to tap in at a point inside the actual plant. So we can tap in at a point inside the model. A model is something nothing but a piece of code, probably a software that I have written. In modern times it is going to be a software. So I can tap in at any signal at any point I like, and I can pass on a suitable commensurate voltage, yeah, as a proxy for that state maybe, right. So now this is my overall structure, and henceforth the analysis that we are going to do is with this structure in mind, yeah, and we will see a lot of beautiful things emerge. So first let us write down the equation of this, yeah, keep this figure in mind. Okay, let me start by writing the equations here itself, so that, so what is x dot? So this is x, this is x dot, this is x hat, this is x hat dot. So let me first write x dot. What is x dot going to be equal to? X dot is going to be equal to ax plus bu, yeah, which is going to be a times x plus b times, note what is coming here, u plus r. What is u? U is kx hat, so it is going to be kx hat plus r, okay. I hope you have convinced yourself that this is indeed true. See, what am I equating here? This is x hat, sorry, x dot. X dot is equal to, this is all summed here, it is b times u, yeah, plus ax. So b times u plus ax, and then what is u? U is nothing but r plus kx hat. So I am just substituting r plus kx hat here. What is x hat dot? Yeah. So now you notice that x hat dot is going to be nothing but a x hat. So I am basically looking at this summary, a x hat, yeah. So that is this channel a x hat plus b times u as before, plus what is happening here is L times y hat minus y, yeah. This is going to be the overall expression, but now of course I have to simplify this, so I can write this as a x hat plus b, remember what u is, it is k x hat plus r plus L, remember this is c x hat minus c x, yeah. Why is c x? Y hat is c x hat, we are assuming that d is equal to 0, yeah, it just unnecessarily complicates the calculations, but you will see that eventually it does not matter, because du minus du will be cancelled out, u is after all the same applied to both the plant and the model, no. So although we are assuming d is equal to 0, if you did not assume d is equal to 0, it would still cancel out here, it would not matter. So now having seen this expression from here, we will carry this forward to the next slide where we have more space. So let me write this out openly. So what we then have is, we can write this in the vectored form, x dot and x hat dot like this, and what we then have is, notice I am going to go back to this slide, we have a times x and bk times x hat. So let me write that down, x and x hat. So remember this is 2n, this is of size 2n, right. So this is a 2n cross 2n matrix, 2n cross 2n matrix. So I have a times x and what do I have, plus bk times x hat. bk times x hat. So sometimes people write minus kx, yeah, it's just a matter of sign, whatever numerical values you get the signs will be inverted. People are fond of using negative feedback, so I am just not bothered about that use, so I am just using this bk and whatever you have here, right. So I am not bothering with that, but the second equation is going to be interesting. See, what is the coefficient of x here? Minus LC, there is no other x appearing anywhere, no, so it is minus LC, and what is the coefficient of x hat? There is a here, there is bk here, and there is LC here, so it is a plus bk plus LC, yeah, so it is a plus bk plus LC. And what about the exogenous input? Well, that is quite simple, it is just going to be this b and b, and you have this r here, yeah, just see that both of them have this b times r and b times r appearing here, yeah. So this is my state equation now in the 2n cross 2n system, the plant states and the observer states taken stacked up together. This is how I can write this up. Now notice that what are my poles? So then I want to find out the determinant of this block matrix, this A, Bk minus Lc and A plus Bk plus Lc. So in the closed loop, all my closed loop poles are given by this, right? These are all my states, no? So if I want them to be determined, then I better evaluate this determinant, yeah? I need to find out what this determinant is, because this matrix is after all my closed loop system matrix, no? Once I have closed the loop around the observer and everything, this is my combined system, there are only 2n states, n coming from the plant, n coming from the observer. So now I want to evaluate this determinant. So remember, this is of size n, this is of size n, this is of size n, and this is of size n, right. So again we are going to use the property of determinant that you add any two rows and their scaled versions, or you take linear combinations, the determinant does not change, yeah. So you add to any existing column some alpha times any other column, the determinant does not change, and that is what we know, right. So we are going to use that property. So what I am now going to say is, you have to be a little careful and pay attention. What I am going to say is, to these first n columns I am going to add the next n columns. What I am saying is, to the first column I am going to add the n plus 1th column, to the second column I am going to add the n plus 2th column, to the third column I am going to add the n plus 3th column, to the nth column I am going to add the 2nth column, yeah, that is what I am doing. And if you just observe a little carefully, this turns out to be nothing but, yeah, so I am going to just add these columns, okay, or let me actually, because I want to find out the characteristic polynomial, so I should actually write Si minus, minus, plus and Si minus, yeah, because I want to evaluate the characteristic polynomial. So this is the characteristic polynomial of the closed loop system, no? Yeah, so I should have written an Si minus, so I just did that, Si minus, sorry about that. So this is the closed loop matrix, so I want to find out determinant Si minus ACL, yeah, so that is exactly this. So it is this Si minus, yeah, so I just change the minus sign here. Now if I want to add, as I said earlier, what I get is this Si minus A, and this is LC. So what I am going to do is, actually I am going to add these columns to this. So I am going to add to the n plus 1th column the first column, the n plus 2th column the second column, likewise to the 2nth column I am going to add the nth column. So I am going to add this. So what I get is Si minus A minus Bk, yeah. See, this is tantamount to adding these block matrices, yeah, that is what you have to see, that is the only key observation, yeah, because after all what is the 2nth column? That is the last column of Bk. What is the n plus 1th column? That is the first column of Bk. What is the nth column? That is the last column of Si minus A. What is the first column? That is the first column of Si minus A. So the first column of this overall matrix, yeah, the first n tuple at least gives you the first column of Si minus A, that is getting added to the first column of minus Bk. So I hope that you agree that this block addition, if it makes you a little uncomfortable even, yeah, how we are adding these blocks, it is basically just the same, right, we are adding this column wise, it is nothing but the usual determinant operation that you are used to. So now what happens is, we get here Si, note that this is a minus sign here, so there is a minus LC, minus Bk, minus A here, and to that you add a plus LC, so this becomes Si minus A minus Bk, yeah, and this is beautiful, because now notice that just like I take factors out common, yeah, I can take out this factor common from here, yeah, so I can take out this factor common from here. This is nothing but Si minus A minus Bk times I, this is also Si minus A minus Bk times I, so I can take this as determinant of Si minus A minus Bk times the determinant of Si minus A Lc I. Yeah, or if you are uncomfortable with that, let me not do this. Let me not make you uncomfortable with this. Yeah, let us just go about it this way. Let us just do the row operation now. Okay. So let me just from the first n rows subtract the last n rows. Yeah. So first we did a column operation. So then what we get is equal to determinant of Si minus A minus Lc, and this is going to be 0 of course, this is going to remain Lc, and this is going to be Si minus A minus Bk. So now if you expand by the determinant, you will see that this is now a triangular matrix, yeah. So a block triangular matrix, and its determinant will be the product of the blocks sitting in the diagonals. This is a well known result, that if one of these blocks is a 0 block, yeah, I mean please note that this is not exactly the same as the usual determinant multiplications that you have seen in case of 2 by 2 determinant, 2 by 2 matrices, right. Block determinants are not, they do not always work that way, but in this case it does. See, if they had worked that way, then what I could have done here is I could have just taken Si minus A times this minus this times this, yeah, it clearly does not work that way, yeah. But only after we have gotten to this stage can we use that result which is analogous to a 2 by 2 matrix, okay. So that is why you might wonder, okay, if this fellow is ultimately doing this minus this minus this minus this, that is exactly like a 2 by 2 matrix, no, but we could not have done this at this stage. There are some properties about commutativity of certain blocks, yeah. So because now there is a 0 block here, so the 0 block commutes with any other block, yeah. So that proof is beyond the scope. You have to again trust me on this. If you are interested, please look up the results on determinants of block matrices, and you will find that there are some commutative properties. If certain blocks commute with certain others, yeah, then you can use the same 2 by 2 like formula for the block 2 by 2 case as well, yeah. In general you cannot, that is why we had to go through all this row and column operation and did not apply the usual 2 by 2 determinant like this times this minus this times this, we did not apply that, right. Okay, so please look that up. So that is the only thing that I am not going to prove here, but ask you to look up. So this turns out to be determinant of Si minus A minus Lc times the determinant of Si minus A minus Bk. And why is this beautiful? Because now note that the roots of the closed loop system are nothing but the union of the roots of the controller taken separately and the roots of the observer, right. So I want you to again cast your attention back to this diagram here. This looks very complicated, yeah. We have this output of the system coming here, we output of the model coming here, we take the difference of those outputs, pass it through a gain block here, feed it to the model here, apparently that is what makes it closed loop observer, yeah, then tap into this state and sort of feed it back here, yeah. We do not even know what the closed loop poles are going to be, but now we see that if I choose, so what are my variables that I can choose here? I can choose this k as I desire, and I can choose this L as I desire. These are two choices, so 2n parameters that I can play around with. The n parameters in the vector k, the row vector k, and the n parameters in the column vector L, yeah. It turns out that this LC, A plus LC will be the closed loop characteristic polynomial for the observer, and A plus Bk will be the closed loop characteristic polynomial for the plant plus controller, right. And it turns out that this tells us that the overall closed loop characteristic polynomial will contain excuse me, all the closed loop poles of the controller, yeah, plant plus controller combined, and all the closed loop poles of the plant plus observer plus the feedback, the closed loop observer combination. So therefore we can independently, through choices of L and K, this is very important, through choices of L and K we can independently design the poles of the observer structure, yeah, the poles of the observer structure, which would allow us to ensure that this is not a problem, that the fact that the error converges fast enough and that the error does not diverge in case A matrix fails to be Hurwitz. See, the A matrix is the plant's matrix, as I said earlier also repeatedly. There is no guarantee that this A matrix is even stable or Hurwitz, right. If it is not Hurwitz, then this error in the open loop observer model would diverge. So therefore it is imperative that we are able to control the dynamics of the observer in closed loop, and this tells us that through use of this L, this feedback vector here, we will be able to place those poles of the observer to wherever we want to, and once we are able to do that, yeah, then we can ensure that not just this error converges, but the error converges as fast as we like, of course asymptotically, so it enters within some 2% band of 0 as fast as we like, if you want to, if you design the observer to be fast enough, right, by choosing the poles of A plus LC to be far enough to the left half plane, right. So this is telling us that the poles of the observer and the poles of the plant plus controller combined can be chosen independently, and this is a big sigh of relief, yeah, this is a big sigh of relief, because this tells us that by designing this observer and this structure, we are not meddling with the original poles that we expect to have with just the plant plus controller, yeah. So what we are saying is that by bringing in this observer structure, we are still retaining that original flavor, like what we had done by initially tapping into the states of the plant that we had proposed the other day, right. We said we tap into the states of the plant and draw those states out from there and then feed them back through this K matrix, and we get A plus BK as our closed loop matrix, right. So those poles still remain intact through our design, right, those poles still remain intact, and the observer poles, they can be designed independently, okay. So that is a big relief, that is what we have seen in this derivation here, but there is still one big question which we should need the answer to, okay. So this is that is the answer we shall see in the next lecture. The question still remains, it is alright, you have proved to me that the poles of the observer and the poles of the controller can be designed independently, so there is a separation between their design. I can choose L to influence the poles of the observer, and I can choose K to influence the poles of the controller, yeah. So you can clearly see that if I want to place the poles of the observer arbitrarily, then I need that this, so earlier I had A plus BK, and now I have A transpose plus C transpose L transpose, no, because remember that the poles of the eigenvalues of this are the same as the eigenvalues of A plus LC. The eigenvalues of a matrix and its transpose are the same. So now what do I need here? So basically if controllability of AB, yeah, invertible, this was my necessity for pole placement of the controller. So then for observer pole design, I need controllability of A transpose C transpose, yeah, but what is the controllability of A transpose C transpose? Yeah, so I need this to be invertible. So for this to be invertible, I need basically C transpose, then A transpose, C transpose, then A transpose squared, C transpose, likewise till A transpose to the power n minus 1 C transpose. But what is this? This is after all nothing but the transpose of the observability matrix, no? Yeah. So basically for the ability to place the poles of the observer anywhere I like, yeah, all the poles, I need observability, yeah. So I need this observability to be invertible. So if the transpose of the observability matrix is invertible, so is the original matrix itself, yeah. So therefore I need observability for designing the observer's poles anywhere I like and make it as fast as I want to, right. But the question still remains, I understand that the poles of the observer are designed independently, the poles of the controller are designed independently. The question, the burning question which I want to leave you with at the end of today's lecture which we shall answer only in the next lecture, is it's alright, I understand that poles are independently designed, but what is the guarantee that if I go from this R to this Y here, that transfer function that I obtain from R to Y is not influenced by these additional poles of the observer, because remember, in my original system that I had designed without this observer and all, before I brought in this observer requirement, even when I said that I am allowed to tap into the plant, what was my closed loop system? Remember many a lecture back, or maybe last lecture itself, I do not recall, when we said this, remember this was my closed loop pole, closed loop like system matrix, no? So my closed loop polynomial, closed loop characteristic polynomial was Si minus A minus Bk, this determinant, this was my closed loop characteristic polynomial, but now what is the guarantee that after adding this observer structure, that some of the poles of this observer are not getting appended and some of the poles of the controller are maybe coming over here, spilling over, I do not know that, right. I only know that the overall poles are nothing but the poles of the controller and the poles of the observer, but what about the transfer function from R to Y? Is it totally unaffected by the poles that I placed of the observer or by all of this design? Is it still pure, in the sense that is it still going to be, so the question is the overall transfer function from R to Y still equal to C times Si minus A minus Bk inverse B, because that is what I need to answer. So this is the question we shall answer in the next class, strongly in the affirmative, thereby sort of convincing you that this observer controller combination does nothing more than what I would have been able to do if I were allowed to tap into the states, but now instead of tapping into the states, I am just passing on the output, and through this beautiful design of the observer and controller combination, I can place the poles anywhere I please. So this is the derivation we shall see in the next lecture. Thank you.